Hello viewers, Wagadarunal taking you through the story of A-Level Physics Paper 2, and this video I'm going to go through the marking guide of the topical tests on reflection at plane and curved surfaces. So where necessary, those constants will be used. So just start with question 1, part A, Roman 1, which says state the characteristics of images formed in plane mirrors, and they give you 2 marks. So 1 is that they are virtual. Next is that they are laterally inverted. Then the image is the same size as the object. And lastly, the image distance from the mirror is equal to the object distance from the mirror. So now we shall go to Roman 2. Roman 2 says differentiate between regular reflection and diffuse reflection. Illustrate your answer with an example and or diagrams. So first we shall draw a diagram for regular reflection. So regular reflection requires a smooth plane surface, so that a ray parallel incident beam gives rise to a parallel reflected beam. So this is a parallel incident beam, and this is a parallel reflected beam. So when this happens, it is called regular reflection. So we shall come and write something and say that if a parallel beam of light is incident on a smooth, this word, smooth plane surface, it is reflected as a parallel beam, and this is called regular reflection. Now because the reflected beam is parallel, it implies that the amount of light intensity after reflection is slightly reduced due to absorption on the reflecting surface. So it is just slightly. They told us also give an example. So an example is reflection by plane mirrors. So that's how marks will be awarded for this slide. So this has been regular reflection. What about diffuse reflection? So for diffuse, we shall need a rough surface. And because it is rough, it implies that a parallel incident beam will give rise to a scattered reflected beam. So when that happens, it is known as diffuse reflection. So let's write something. So here we shall come and say that if a parallel beam of light is incident on a rough plane surface, it is reflected in different directions from the surface, and this type of reflection is known as diffuse reflection. Now because the reflected beam is scattered, it implies that the amount of intensity will reduce. So the amount of light intensity after reflection is much low due to absorption and scattering of the reflecting surface. Remember, for regular it was only due to absorption, so the loss in intensity was small, but here it is much. So the example is reflection by a piece of paper. So a piece of paper, however smooth it may be, it still has some roughness. So that's how marks would be awarded. So now we shall go to part A, Roman 3. It says that with the aid of a diagram, Describe the operation of an optical lever in a mirror galvanometer. So what we need to know is that an optical lever in a mirror galvanometer is used to measure small electric current. So small electric current by making use of a small spot of a beam of light as a pointer. So it is easily explained when you use a diagram. So let's first draw a diagram and the description will be easier. So that is the graduated scale. Then you also have a fixed lamp. Then you have a plane mirror M1 there. So light incident normally will be reflected back along the same path. Now when you pass current, the mirror will rotate by an angle, say theta. So when it rotates, it implies that now the incident beam will be reflected in a different direction. Why? Because it no longer hits this mirror normally. So this one was reflected along the same path because this was 90 degrees and this was also 90 degrees. But when this mirror is rotated due to the small current passed, it implies that now when it will hit the mirror not at 90 but at an angle. So that means that the reflected beam will be in that direction. So what we need is this distance, this and also this. Now I think realize that when this is theta, this will be 2 theta. It is a property that the angle of rotation is twice the deviation of the reflected ray. So that diagram we can now go ahead to describe our description. So a small plane mirror M1 is rigidly attached to a system which rotates when current flows through it, and a beam of light from a fixed lamp shines on the mirror as shown in the diagram. So 1 mark will be for the correct setup. Now let's go to the next slide. So you come and say that if the light is incident normally or perpendicular on the mirror at A, the beam is reflected directly back along the same path and a spot is obtained at O on the graduated scale placed just below the lamp. So that's what we had explained earlier. This beam is reflected back along the same path to give a spot at O. So now the question is, what happens when current is passed through the system? So Shakama says that when a current I is passed in the system, the mirror rotates through an angle theta to position M2, and the spot of light is deflected through a distance x to position P on the graduated scale. So this was this other ray here deflected to a position P by a deviation x. So the rotation of the reflected ray is twice the angle of rotation of the mirror. I think we already know that property, so that means that tan 2 theta will be equal to dx over d, because we know that tan is equal to opposite over adjacent. Therefore, when the angle is this one, it means that the opposite is here and the adjacent is this. So that we shall say that for small angles measured in radians, it implies that tan an angle is approximately equal to that very angle. Therefore, tan 2 theta will be approximately equal to 2 theta. Now when I substitute that, I'll come up with 2 theta equal to x over d. Then I'll conclude and say that since alpha is proportional to theta, the current flowing through the system can be determined. So basically that's how an optical lever galvanometer works. So now we shall go to part B, Roman 1. So Roman 1 says that what is meant by radius of curvature of a concave mirror? So the radius of curvature of a concave mirror is the radius of the sphere from which the spherical surfaces of the mirror is cut. Alternatively, you can say that this is the radius of the sphere of which the spherical surfaces of the mirror forms part. So the difference is in these two words, but all mean the same. So now we shall go to part B, Roman 2. Roman 2 says, show that the radius of curvature r of a concave mirror is given by the expression r equal to 2f, where f is the focal length of the mirror. So the derivation is easily done with the aid of a diagram. There's no way you can derive without a diagram. So let's first draw a diagram and then we can derive the relation. So this is a symbol to mean a concave mirror or converging mirror. Capital C will be the center of curvature, this one will be the principal focus, therefore this is the focal length and this is the radius of curvature. P is the pole of the mirror. So you shall consider ray parallel and close the principal axis, that is ray AB. So a ray is noted by an arrow. Without an arrow, it is no longer a ray. So when it is parallel and it is this, it will be reflected to pass through the principal focus, as you can see it here. So like I said, a ray is a ray if it has an arrow. So without an arrow, it is no longer a ray. Now this one, I think realize that this one, it does not have any arrow and it will act as our normal, because this is the center of curvature and this surface is spherical. Therefore the angle of reflection, angle of incidence is equal to the angle of reflection. Therefore if this is alpha, this will also be alpha. Then you also know that alternating angles are equal, so this angle will be equal to this, and the reason is because they are alternating. Then next is the exterior angle property. Two opposite interior angles are equal to one exterior angle. Therefore alpha plus alpha will be equal to this, which gives you 2 alpha. So you're done with the red diagram. Now we can use it to derive our relation. So first we have said that array AB parallel and close. So this word is needed. Parallel and close. to the principal axis is reflected to pass through the principal focus capital F. So what does that mean? It means that FP is equal to the focal length of the mirror. Then we shall say that if C is the center of curvature of the mirror, then BC is the normal at B, and CP is the radius of curvature of the mirror. I think I already showed you that. If you look at this, and that is the only reason why we didn't put an arrow here, because this is no longer a ray but is acting as a normal, because it is passing through the center of curvature. The next is to make an assumption. So assuming that alpha is a small angle expressed in radians. I think we already know that assumption. When an angle is small, it implies that tan that angle approximates to that very angle. So what does that mean? It means that alpha is approximates, now here we use approximates to tan alpha, but you already know that tan alpha is BP over CP. Why? Because tan is opposite over adjacent. So when you go here and we look for tan alpha, it means that I'm going to use the triangle CBP. And when I use that triangle with this angle here, opposite to be this, which is BP, and adjacent is CP. What about tan to alpha? For tan to alpha, we use the triangle CBF. With that, I'll realize that this is BP is the opposite and FP is the adjacent. Therefore, tan to alpha is equal to BP over FP. So that is where these ratios are coming from. But you should be keen of this approximation sign. Be keen of this approximation sign. So the good thing we already know that FP is focal length and CP is radius of curvature. Now what I'm going to do, I'm going to substitute for alpha. So this value, this alpha here, will be substituted here to come up with 2 times this. This 2 is here, and where there is alpha, we are going to put there this, which is this, and we said is equal to this, so I'll come and put it here. So when I cross multiply, first of all, you realize that this BP and this BP can cancel. Therefore, I remain with 2 over CP is equal to 1 over FP. So when I cross multiply, I'll come up with CP equal to 2FP. But I already saw that CP is equal to radius of curvature and FP is equal to focal length. So basically, this is the derivation they wanted us to get. So that's how the marks would be awarded. So now we shall go to part C. Part C says, explain why a paraboloid mirror is used in searchlights instead of concave mirror. So paraboloid mirror is the same as a parabolic mirror, so it's the same word. It shouldn't confuse you. So a paraboloid mirror reflects all the light rays from a light source at its focus. So note this word, the source must be the focus, and when the source is the focus, all the light rays will be reflected as a perfectly, this word is needed, perfectly parallel beam. When that happens, what is the use of it? So in this case, the intensity of the reflected beam is practically undiminished at longer distances because it is a parallel beam. What about for a concave mirror? For a concave mirror, if you place the source at the focus, it will produce a parallel beam closer to the axis only. But the rays which is far from the principal axis, they will give rise to a divergent beam. Now because we have we have a parallel beam and a divergent beam, it implies that the intensity will reduce with time. Therefore, we shall come and say that this reduces the intensity of the reflected beam at longer distances from the reflector. So that's how the marks would be awarded. So that was question 1. Now we shall go to question 2. So question 2, part A, Roman 1 says, distinguish between real and virtual images. So you come and say that a real image is an image formed by actual intersection of light rays, while a virtual image is one which is formed by apparent intersection of light rays. So the keyword is here is actual and here it is apparent. So that was Roman 1. Now we shall go to Roman 2. Roman 2 says, describe how the position of an image in a plane mirror can be located. So still it is easily explained with an illustration. So we have a plane mirror and an object. Now we need to locate the image of this object. So you shall draw this diagram with step by step with the explanation. So let's first see the first line of the explanation on this slide. So here they told us that an object pin O is placed in front of a plane mirror M, placed on a white sheet of paper fixed on a soft board, as you can see it here. So this is the plane mirror and this is the object pin O, this dot you see. That was the first line. What about the second line? We shall come and say that looking through side A of the mirror, two pins P1 and P2 are placed so that they appear to be in line with the image of pin O in the mirror. So what you're going to do, you look through this side A and locate the image of the mirror. So you place pin P1 and pin P2 so that they appear to be in the same line with the image. So if the image is here, they should be in the same line. So that was line 2. What about line 3? Line 3 says the experiment is repeated with pins P3 and P4 on side B. So what does that mean? It means that now, previously you are looking from side A, now you shall look from side B and locate also two pins P3 and P4 so that those two pins are in the same line with the image. That was line 3. Now what about line 4? For line 4 we shall say the pins and the mirror are removed and lines drawn through the pin marks of P1, P2 and P3, P4 to meet at I. So I is the point of intersection. So we shall come here and say, so you remove the pins and then you draw a line to join P1 and P2 and that will be the line. Then also draw a line to join P3 and P4 and that will be the line. But they talked about the intersection. So what we are going to do, you will elongate this line and also elongate this line so that they meet at a certain point. Now that point we shall call it point I. So yeah, we shall come and say that the point I where they meet is the location stroke position of the virtual image. So So basically that's what they wanted. Now for this slide, that's how marks would be awarded. What about for this other slide? So that's how marks will be awarded for that slide. So now we shall go to part B. Part B says, the diagram in figure below shows a ray of light undergoing two successive reflections at point X and Y in two mirrors M1 and M2, inclined at an angle theta. So these are the two mirrors, and this is the angle of inclination of the two mirrors, and these are the points where the ray undergoes reflection. Show that the ray is deviated through an angle to theta. So we shall first redraw the given diagram, and we shall add on something which will help us to get the required derivation. So that was the given diagram. We are going to add on something. What we are going to add is that if this is alpha, it implies that this one is also alpha. They are glancing angles. Then when I elongate this line, I realize that this and this are vertically opposite angles. So if this is alpha, this will also be alpha. That is at point X. What about at point Y? At point Y, if this is the glancing angle, it implies that this is also beta, and also when I elongate, this will also be beta, vertically opposite angles. So with that, we shall go ahead and do our derivation. One, we shall say, suppose the glancing angles at X and Y are alpha and beta. So this is the glancing angle at X, and this is the glancing angle at Y. From triangle X, Y, Z, X, Y, and Z. So Z, we didn't show it, but it should be here. So you put that Z there. So from triangle X, Y, Z, it implies that, remember, angles of a triangle add up to 180. So this plus this is equal to 180. That's what this one means. Then when I take this theta this side, I'll come up with beta plus alpha being equal to 180 minus theta. Then we shall also say that the deviation produced by reflection at X is 2 alpha clockwise, and that at Y is 2 beta clockwise. So deviation, remember originally this ray was moving in this direction, but now it has been deviated from here to reach here. So this is what we call the deviation. I think we see that the arrow is clockwise. That's why there is this word clockwise. Then this 2 alpha is got by adding these two angles, this plus this, to give you the total deviation as 2 alpha. Similarly for at Y, it was originally going this direction, so it was deviated to be in that direction. Therefore, I think we realize that it is also clockwise. That is why there is this word clockwise. Then the 2 beta is got by adding this plus that to give you 2 beta. So that was the deviation at each mirror. So the total deviation will be got by adding the 2. Because they are all in the same direction, we'll have the same sign. So clockwise means that they can all be positive, but this word has to be seen. After that, I'll factorize out 2 to come up with beta plus alpha. Then I'll remember that beta plus alpha is equal to 180 minus theta. Therefore, I'll come and substitute for that to come up with the total deviation in clockwise direction as 2 in brackets 180 minus theta. When I open brackets, I'll come up with 360 degrees minus 2 theta. Then I'll remember that 360 degrees is 0 deviation because you have come back from where you started from. If, for example, if I started from here and I move 360, I'll have gone back to where I started from, so there will be 0 deviation. What does that mean? It means that the total deviation in a clockwise direction is negative theta, negative 2 theta. Now if in clockwise it is negative, it implies that in anti-clockwise it will be positive. Therefore, come and conclude that total deviation is positive 2 theta in an anti-clockwise direction. So that's how the marks would be awarded. So now we shall go to part C. Part C says, derive an expression relating the focal length f of a convex mirror to the object distance u and image distance v. So this derivation can be done in two ways. One, you can use a point object, or you can use a finite object. Now in this question they didn't specify whether I should use a point object or a finite object. So what we are going to do, both approaches will be used and you'll learn how to derive using both, using a point object and also using a finite object. So what we are going to do, let's start with the one for a point object. So like I said, there's no way you can run away from a ray diagram. So what you're going to do, we are going to consider a ray of light from a point O incident on the mirror at A. What happens? The ray is reflected to form a virtual image I on the principal axis of the mirror as shown below. So we are going to draw a ray diagram to show that information. So this O is the object, P is the pole of the mirror, C is the center of curvature, U is the object distance, R is the radius of curvature. So a ray from the object will be reflected by the mirror. So when it reaches this, when it is incident on this mirror, remember this is the center of curvature, meaning that this will act as the normal. So that explains why you don't see any arrow here. So a ray is a ray when there is an arrow, but you should be keen not to put an arrow here. So let this angle be theta and this one be alpha. So next we shall remember that angle of incidence is equal to angle of reflection. That is why here, if this is lambda, this will also be lambda, and this will be the reflected ray. Now this reflected ray will appear to come from a certain point, and that point where it appears to come from will be the position of our image. So I think you realize that this dotted line is dotted because the image will be virtual. Then also this angle and this angle are the same, vertically opposite angles. So yeah, come and say that according to Rio is positive sign convention, object distance OP is equal to positive U, image distance IP is equal to negative V, because I think we realize that this is dotted, and focal length CP is also negative, and AP is H. So from here to here the height is H. So by Rio's positive sign convention for this diverging mirror, the image is negative and also the radius of curvature is negative. Then by geometry, using triangle AOC, when I come here AOC, using that triangle, you realize that this lambda is equal to theta plus alpha. Why? Because we are going to use the exterior angle property, whereby this exterior angle is equal to the sum of two opposite interior angles. So the opposite interior angles are theta and alpha. What about for triangle AOI? So A, O, and I. AOI. So the exterior angle is 2 lambda and the interior angles are theta plus beta, theta and beta. Therefore 2 lambda will be equal to theta plus beta. So for this slide, those are the marks. Now we shall go to the next slide and continue with the derivation. So equation 1 multiplied by 2 minus equation 2 gives, so remember the relationship is between the image distance, object distance and the focal length. Therefore this lambda is not part of them. Therefore we have to look for a way of eliminating lambda in these two equations. So to do that, we are going to first multiply 2 throughout this equation to come up with 2 lambda, 2 theta and 2 alpha. Then after that we shall subtract. So this minus this is 0, this minus this is theta, this minus this is 2 alpha minus beta. So let's come and do that. So I'll come up with 0 equal to theta plus 2 alpha minus beta. Put 2 alpha on the other side. So what I'm going to do, I have brought this beta here to become positive and also this theta here to become negative. That's why you see here beta minus theta. So now assuming that these three angles are small and they are expressed in radians, we shall come up with alpha will be approximately equal to tan alpha, but tan alpha is AP over CP. So let's first use that. So tan alpha, the opposite is here, which is AP over CP. What about tan beta? Tan beta opposite is AP over PI or IP. Then tan theta will be equal to AP over OP. So tan alpha alpha approximates to tan alpha, and tan alpha is AP over CP, but we already saw that AP is H and CP is negative R. What about beta? Beta approximates to tan beta, and tan beta is AP over IP. We saw that AP is H and IP is negative V. What about theta? Theta approximates to tan theta, and tan theta is AP over OP, where AP is H and OP is U. So what I'm going to do, I will substitute for this value of alpha, beta and theta in this equation 3 to come up with that. So H is common, it can cancel throughout. Then also negative is common because this is negative here, negative here and negative here, so it can cancel to come up with positives. So it will be now 2 over R equal to V over 1 over V plus 1 over U. But we already know that F is equal to R over 2, therefore when I substitute for this, I'll come up with 1 over F equal to 1 over U plus 1 over V. So basically that is what they wanted. So that is the option for a point object. What if it was a finite object? So for a finite object, we shall consider array AB from a finite object incident on a concave mirror at B. This ray will be reflected and it will appear to come from a point F, capital F, behind the mirror. That is a ray when the ray is parallel. What about this array from A through the center of curvature C? Is this ray will be reflected along its own path. So let's see that in array diagram. So we have this as the pole of the mirror. This is the principal focus. This is the focal length. and this is the center of curvature. So that is our finite object O, and U is the object distance. Therefore, a ray parallel and close to the principal axis is reflected to appear as if it is coming from the principal focus, capital F. Then a ray through the center of curvature is reflected along its own path. So you should be keen of the part which is dotted and the part which is not dotted. So the image will be this, and to be upright, virtual, and diminished. So this, the V is the object image distance, U is the object distance, F is the focal length. Now I want the relationship between those three parameters. So according to Rio's positive sign convention, AP is equal to U, which is the object distance, image distance IP is negative V, and focal length FP is negative F. So here we shall see the triangle AOC, A, O, and C. Then triangle CIQ, C, I, and Q. They are similar because they share a common angle. I think we can see that this angle is common for both triangles. So what does that mean? It means that the ratio of OA over IQ, the ratio of their heights, is equal to OC over IC because of similarity. But the good thing I know that OC, this OC from here up to here, how can it be got? We know that from here to here is U. Then from here to here is the radius, which is twice the focal length. That is why you see here U plus 2F, but a negative, because we say that focal length is negative by Rio's positive sign convention. What about IC? IC. This IC, the good thing I know this one, which is V, and I know the whole of this, which is negative 2F, but that means that when I subtract the 2, I'll be able to get the IC. Therefore, IC will be equal to this one, which is negative 2F minus negative V, to come up with this over that. So those two triangles were similar. Now also triangle IFQ and FBP are similar. So let's first see those ones. IFQ, so IFQ and FBP, they are similar because they share an angle. Therefore the ratio of their heights and their lengths will also be equal. So we shall come here and say that PB over IQ is equal to PF over IF. When I substitute PF is negative F and IF is negative F minus negative V, so this one gives me this and this gives me that. So to make this one positive, I can rearrange by multiplying both sides by negative 1, multiplying up and down by negative 1. When I do that, this becomes positive, then this F becomes positive, and this one becomes negative. But I know that OA is equal to PB. So when you come back here, this OA and this PB, they are the same because this ray is parallel. So that, what does that mean? It means that these two ratios will be the same. This one will be equal to this ratio. But in the previous slide we saw that this ratio is this, and in this slide you have seen that this ratio is that. So I'm going to equate the two. So when I equate the two, the next thing to do is to rearrange and get the required expression. So let me start by cross multiplying. So when I cross multiply, I come up with this, then open brackets to come up with that line. Then here I realize that this one and this one can cancel, then this and this can be reduced, so to come up with that. So what I'm going to do, I'm going to divide throughout by UVF, and that will give me this. Reduce to come up with this. So this UF and UF will remain with 1 over V, which is that. UV remain with 1 over F, which is that. VF will remain with 1 over U, which is that. Then rearrange to get the required expression, which is that. So basically that is what they wanted. So that's how we could then marks for that slide. What about for this slide? For this slide, that's how you could get the marks. So any of the two approach is okay. So now shall go to part D, Roman 1. Part D, Roman 1 says, a concave mirror forms an image half the size of the object. So that means that the magnification is half. The object is then moved towards, not this word, towards the mirror. In other words, the object distance has been reduced until the image size is 3/4 that of the object. So the new magnification is now 3/4. If the image is moved by a distance of 6, calculate Roman 1 the focal length of the mirror and Roman 2 the new position of the object. So case 1 before displacement, we shall use that formula. I think you know it. M magnification is equal to V over F minus 1. So the first magnification was a half. This one we don't know it, and this one also don't know it. So we shall make it the subject. So V1 over F will be 3/2 when I bring this one this side. So I'll first leave that one there and go to case 2 after displacement. So that means that the new magnification will be equal to the new V over F minus 1. I know the new magnification is this. Now the new V, or the new image distance, remember when the object distance is reduced, the image distance will be increased. Now because they told us that the displacement was 6, it means that for it to increase, you'll get the initial image distance and you add on the 6, which is the displacement. When I split the numerator, this one will give me this. Then from there, remember that V1 over F is equal to 3/2. So I'll come and substitute to come up with that. So now I have only one unknown. I'll have to simplify and make it the subject. So cross multiply, F will be 24 centimeters. So that was Roman 1. What about Roman 2? Roman 2 says that find the new position of the object. So the new position will be 1, we shall get it. This is the formula for magnification, object distance, and focal length. So 1 over M is equal to U over F minus 1. So the new magnification was 3/4, so its reciprocal will be 4/3. This one is what they want. Focal length, we have got it as 24. So the next thing to do is make you the subject, and you will be equal to 56 centimeters. So that's how marks will be awarded. So now shall go to question 3. A Roman 1 says, what is meant by radius of curvature of a convex mirror? So you come and say the radius of curvature of a convex mirror is the radius of the sphere from which the spherical surfaces of the mirror is cut. Or you can say that this is the radius of the sphere of which the spherical surfaces of the mirror forms part. So that was Roman 1. Now we shall go to Roman 2. Roman 2 says, describe an experiment including a graphical analysis. Note this word, including a graphical analysis of the results to determine the focal length of a concave mirror using the no parallax method. So we shall need a diagram of the setup to help us is the explanation. So we shall start with the mirror, then we also need the object. Then we also, when this is the object, this will be the image. Remember, when the object is upright, the image will be inverted. Now this image will be searched using the no parallax method. So we shall need an observer and then the search pin. So the search pin will be that. So that search pin is used to search this image until they coincide. That's why they call it no parallax method. And the distance between the two will be now v, which is the image distance. So let's look at the description. So you have said that an object pin O is placed at a distance u greater than, this condition, greater than the estimated value of the focal length with its tip along the principal axis of the concave mirror. Concave mirror M mounted vertically in a holder. Now if the distance u is not greater than the estimated value of the focal length, the image will not be seen. That is why it has to be greater. So you keep on adjusting the u until it is greater. That's how you'll be able to focus the image. Other we shall say that the image I of pin O is observed in the mirror, and a second pin S, or the search pin, is used to locate I. Just like I showed you here. So this is the search pin which is used to locate this image I. So pin S, which is the search pin, is moved until there is no parallax between it and the image I. Then from there, the distance v of S from the mirror M is measured and recorded. Now because they taught about graphical analysis, you have to repeat the procedure. So we shall come and say that the procedure is repeated using other object distances u, and the results are tabulated including values of 1 over u and 1 over v. A graph of 1 over v against 1 over u is plotted, and the intercepts on the axis are read and recorded as shown below. So let's first see marks for this slide. So now we are going to plot a graph of 1 over v against 1 over u, and it will be a straight line with intercepts C1 and C2. So let's analyze this graph. So using intercept C1, that means that 1 over u is 0. So from this mirror formula, 1 over u will be 0 and 1 over v is C1. Therefore f will be 1 over C1. Similarly, using intercept C2, it implies that 1 over V is 0 and 1 over U is C2. So you'll come and substitute that to get F as 1 over C2. Then we are going to add the two equations to come up with 2F equal to 1 over C1 plus 1 over C2. When I make F the subject, I'll come up with F being equal to a half of 1 over C1 plus 1 over C2. Therefore, in summary, we shall conclude that the average of the reciprocal of the intercepts is equal to the focal length of the concave mirror. So basically, that is what they wanted. So now we shall go to part B. Part B says, a concave mirror capital M of focal length 20 centimeters is placed 90 centimeters in front of a convex mirror N of focal length 12.5 centimeters. An object is placed on the common axis of M and N at a point 25 centimeters in front of M. Determine the distance of capital N of the image from capital N of the image formed by reflection first in M and then in N. Note this order: the reflection is first at M followed by N. In other words, is first at the concave mirror followed by the convex mirror. So let's first do that Roman. So such a question is easily done by making a sketch of the ray diagram. However, even if you don't make a sketch of this ray diagram, you'll still get all the marks. But for the easy explanation, let's make the sketch. So you have two mirrors, the converging mirror and the diverging mirror, and the distance apart is 90 centimeters. So the object was placed at a distance 25 centimeters from mirror M, and they told us reflection is first at this mirror M followed by mirror N. So this image, the reflection at this mirror, at this converging mirror, will form an image at a point I1. So in absence of this mirror, this ray would have gone up to this point and that would be the image. But because this mirror is there, I think you realize that from here to here the line is dotted. What does that mean? It means that now this image is virtual. And because it is virtual, it will act as the object, and so that forms the final image at this. So this image acts as the object for this mirror. Then when it is the object, it will form an image at this point, and that will be the final image. So that is a ray diagram, but like I said, it is not a must for you to draw it as long as you were conscious of the calculations. So let's see the calculations. So we shall start with concave mirror or mirror M. We know that focal length is 20 and object distance is 25. Therefore, we shall use mirror formula to get the image distance, and image distance will be 100 centimeters. So that's how the marks will be awarded for that slide. Now let's go to the next slide. So like I said, this image acts as the object of the mirror N. Therefore, from here, let's first explain that. From here up to here is 100, but from here up to here is 90. That means that the remaining part is 10. Therefore, this U2 is 10. But you have to remember that this line is dotted. In other words, this image is virtual. Now, because it is virtual, it implies that U2 will be a negative. So let's go and do that in the next slide. So this is the remainder of what I've been explaining. So we shall come and say that for the convex mirror N, focal length is negative because it is a diverging mirror, and the image is also, that object is now negative 10 as I've explained. So we shall come and use mirror formula to get V2, and V2 will be 50 centimeters. Therefore the distance of the final image is 50 centimeters from N. So that was Roman 1. Now we shall go to Roman 2. So Roman 2 says, find the magnification of the image formed in C Roman 1. So magnification, total magnification is the product of the individual magnifications. So this is for the first mirror, this is for the second mirror. So when I get for the first mirror, multiply by the one for the second mirror, I'll come up with 20 as the required magnification. So that's how marks would be awarded. So now shall go to part C. So part C Roman 1 says, show that the image found in a plane mirror is as far behind the mirror as the object is in front. In other words, they want you to show that object distance is equal to image distance. So we shall consider a point object O placed in front of a mirror. Rays of light from O are reflected from the mirror and appear to come from I, which is the virtual image of O as shown below. So we need an illustration to easily derive what we want. So that is the plane mirror, that is the point object. So a ray incident normally at N will be reflected along the same path. What about a ray incident at an angle? It will be reflected such that the angle of incidence is equal to the angle of reflection. So when I elongate those lines backwards, I'll be able to get the point of intersection. I think you remember that under the description for locating an image formed by a plane mirror. Then from there, I'm going to use some geometry. So I'll start with the law of reflection, that angle of incidence is equal to angle of reflection. Therefore, this angle I is equal to angle R, which is this line. Then next I'll say that alpha is equal to I. So this alpha is equal to I, and reason is alternating angles. The next is beta is equal to R, reason is corresponding angles. So because this I is equal to alpha, that means that this one can come here, and this R is equal to beta, meaning that this can come here, meaning therefore we'll come up with angle alpha equal to angle beta. So what does that mean? We shall come and say that since NP is common to both triangles, NPI and ONP, the triangles are congruent, and that means that ON is equal to NI. So basically that is what they wanted. So now we shall go to part C Roman 2. It says that when you look in a mirror, you are able to see the image of your face, but when you look onto the wall, you can't see your face, you can't see your image, and they want you to explain why. So this explanation needs the knowledge of regular and diffuse reflection. So we have said that light rays from the face are parallel, so that when they strike a mirror which is highly polished, the rays will be reflected as a parallel beam, thus forming an image. So that is regular reflection. However, for the wall, A wall has some irregularities, in other words, it is rough. What does that mean? It means that a parallel beam from the face will be reflected as a scattered or non-parallel beam, hence the image can't be seen. So this is diffuse reflection. So you can't see your image in a wall because of diffuse reflection, and you can see your image in a plane mirror because of regular reflection. So that's how the marks would be awarded. So that was question 3. Now shall go to question 4. Part A says, define the focal length of a concave mirror. So focal length of a concave mirror is the distance between the pole of the mirror and the point where rays originally parallel and close to the principal axis converge after reflection from the mirror. So now shall go to part B, Roman 1. Part B says, an object is placed at a distance u from a concave mirror. The mirror forms an image of the object at a distance v. Draw ray diagrams to show the path of light rays when the image formed is real, and Roman 2, virtue. So this is the principal focus, and this is a symbol for a converging mirror. Therefore, we shall have a finite object, then we shall start drawing a ray parallel to the principal axis. It will converge to pass through the principal focus. What about a ray passing through the principal focus? It will be reflected as a parallel beam, which is a ray which is parallel to the principal axis. Now they will intersect at this point. That means that it is the position of the image. So the image will be inverted and diminished. What about for formation of a virtual image? So formation of a virtual image, the object must be in between the pole of the mirror and the principal focus. So a ray parallel will be reflected to pass through the principal focus, and the one through the center of curvature will be reflected along the same path. When I extrapolate the two rays, I think realize that I'm using dotted lines, I'll get a point of intersection, and that will be the position of the image. So the image will be upright and virtual. So that's how marks would be awarded. So now shall go to part C. Part C says, use a geometrical ray diagram to derive the relation 1 over f is equal to 1 over v plus 1 over u for a concave mirror. So still here they didn't specify whether to use a point object or a finite object, so we are going to look at both approaches. So let's start with the point object. So we shall consider a ray of light from a point object O incident on the plane mirror at A. The ray is reflected to form an image I on the principal axis of the mirror as shown below. So we shall draw a ray diagram to help us in the derivation. So there's no way you can derive without a ray diagram. So r is the radius of curvature, and this is the object distance. This is the center of curvature, this is the position of the object, this is the pole of the mirror. So that ray incident will be reflected, so we have to first get the normal. So the normal passes through the center of curvature, therefore the reflected beam will be there such that this angle of incidence is equal to angle of reflection. That's why you see here lambda. So like we did under diverging mirror, only that in this case for converging mirror all are positive. So that is why you see OP is U, positive U, IP is positive V, CP is positive R. Therefore by geometry I'll come and say that for triangle AOC, exterior angle property, this alpha will be equal to this plus that, which is equation 1. Then for triangle AIC, this beta will be equal to these two angles. That is why you see here that equation. So those are the marks for that slide. Next is so we are still going to eliminate lambda. So let's go and eliminate lambda in the next slide. So we shall just subtract equation 2 from equation 1 to come up with alpha minus beta equal to theta minus alpha. Rearrange, take this one this side and this one this side to come up with this equation 3. Then I'll make an assumption. I think remember that assumption for small angles measured in radians, tan alpha is that, theta is that, and beta is that. So I'm going to substitute those values in this equation 3 to come up with that. Then H is common, like we already explained, so I'll come up with that. Then I remember that F is equal to R over 2, so I'll come up with the required expression. So that's how marks will be awarded. That was for a point object. Now we shall go to the approach 2, which requires a finite object. So consider a finite object AB placed perpendicular to the principal axis. Rays of light from the object are reflected by the mirror to form an image I as shown below. So we still need a ray diagram to be able to derive. There is no way you can derive without a ray diagram. So this is the pole of the mirror, this is the principal focus. Then next we need the object, which is finite. So U will be the object distance. So a ray parallel will be reflected to pass through the principal focus. What about a ray through the principal focus? It will be reflected as a ray parallel to the principal axis. So this point of intersection is the position of the image, so we shall come and draw our image there. After that, we shall come and say that AP is U, IP is V, FP is F. Now these two triangles are similar, AB, ABF, and FDP. Why? Because this angle is the same, they share a common angle. Therefore the ratios AB over PD will be equal to AF over PF. But I know that AF from here to here, I can get it by saying that from here to here, which is U, minus from here to here, which is F, to come up with U minus F. Then PF is the focal length, so it will be small f. What about these two triangles, IFQ, and CFP? So they are the same. They are similar because they share a common angle. Therefore, I'll say that PC over IQ is equal to FP over IF. FP is the focal length, IF is V minus F. But AB is equal to PC, so AB is equal to PC. Therefore, it implies that these two ratios will be the same. So before we go to the next slide, let's see marks for this slide. Then next we are going to equate. Now we are going to equate this to this. So let's see that in the next slide. So when I equate, I'll come up with that. Cross multiply, I'll come up with that. X open brackets, come up with that. Collect like terms, then rearrange and divide throughout by UVF to come up with that. In the end, you shall come up with the required expression. So that's how marks would be awarded for a finite object. So now we shall go to part D. Part D says a concave mirror of radius of curvature 40 centimeters contains a liquid to a height of 2 centimeters. A pin clamped horizontally is viewed from above. A pin clamped horizontally and viewed from above is observed to coincide with its image when it is 27 centimeters above the surface of the liquid. Calculate the refractive index of the liquid. So we know that refractive index is equal to real over apparent. Therefore, real over apparent is R minus D over H. So R is this and HD is that, the depth of the water, and H is 27. Therefore, when I divide, I'll come up with 1.41. So now shall go to part E. Part E says you are provided with the following pieces of apparatus: a screen with cross wires, a lamp, a concave mirror, and a meter rule. Describe an experiment to determine the focal length of a concave mirror using the above apparatus. So the first thing to do is to rearrange the apparatus in a way that can help us to get the focal length. So first of all, we shall need a lamp or a source of light, that is the lamp. Then we shall need a cross wires, screen with cross wires. Then we shall also need the mirror placed on a holder. So the distance has to be measured from the pole of the mirror, which is this, up to the screen. So let's see how the apparatus is used, but before that, that's how the marks would be awarded. So this one for the formula, this one for subtraction to get the real depth, and this one for division, and this one for the output. So you come and say that a lamp is placed directly behind the hole with cross wires in the screen. The concave mirror is placed in front of the screen as shown above. I think you already saw it. The position of the mirror is adjusted until a clear image of the wire gauze is obtained on the screen besides, know that word, besides the object. The distance small r of the screen from the mirror is measured using a meter rule. The procedure is repeated twice and the mean value of r is obtained. The focal length f of the mirror is thus got from f equal to r over 2. So in other words, this distance you measure when a clear image is formed besides the cross wires is what we call the radius of curvature. So that was question 4. Now we shall go to question 5. Question 5, part A, Roman 1 says, state the laws of reflection of light. So the first law we shall say that the angle of incidence is equal to the angle of reflection. Then next we shall say that the incident ray, reflected ray, and the normal at the point of incidence all lie in the same plane. So this should be in and not on, as I previously said. So this one should be in the same plane. So you should make that correction in the solutions for beginning of term 3 of S5. So now we shall go to Roman 2. Roman 2 says, a ray of light is incident on a mirror, on a plane mirror. The mirror is then turned through an angle alpha, keeping the direction of the incident ray constant. If the reflected ray turned through an angle beta, find the relation between alpha and beta. So you also draw the diagram step by step, so as we go through the explanation, the derivation. So let's see the first line. So this one says that with a plane mirror still in position M1, the incident ray AO is reflected along OB1. So this is the plane mirror still in position M1, and this is the normal. So the incident ray O is that one, and to be reflected along OB1, so that will be the reflected ray, which is OB1. So that was the first line. Second line says that if theta is the glancing angle, it implies that the deviation D1 is equal to angle COB1, which is equal to theta. So let's first put the glancing angle. That will be the glancing angle theta, and therefore the deviation will be D1, so that is D1, which is COB1, and is equal to 2 theta, because this angle is equal to this angle, and also this angle is equal to that very angle. Therefore theta plus theta will give you 2 theta. So that was line 2. What about line 3? So line 3 says, when the mirror is turned through an angle alpha, the position M2, an angle alpha to position M2, the new glancing angle will be alpha plus theta, and the new deviation D2 will be COB2, which is 2 in brackets alpha plus theta. So let's look at that. So now we are going to turn the plane mirror through an angle alpha to position M2. So this is the angle through which the mirror has been turned. It was here, now it is here, through an angle alpha. So the new glancing angle will be, remember this one is still at the same place, so from here up to here it will be theta plus alpha. That's why you saw here glancing angle as theta plus alpha. Then the new deviation will now be, so the reflected ray will be that OB2, and the new deviation will be D2, which will be twice this angle. And beta will be the angle between the two reflected rays. So for this slide, those are the marks for this slide. So we shall now come here and say that angle beta through which the reflected ray turns is given by D2 minus D1. But D2 is equal to this, and D1 is equal to that. So I'll subtract the 2, simplify, I'll come up with that as the relation between beta and alpha. So that's how marks will be awarded. Now we shall go to part B. Part B says that describe how a sextant is used to determine the angle of elevation of the star. So this one is easily done with the aid of a diagram. So let's first draw a diagram to help us make the description. So that is the setup like I've already done. We shall go complete the diagram step by step as we go through the explanations, description. So let's first see what line 1 has to say. So line 1 says H prime is the view of the horizon as seen directly through the unsilvered part of mirror M1. So what does that mean? It means that this mirror, I think if you are keen with this mirror M1, it has a part which is silvered and a part which is unsilvered. So through the part which is, and this is the observer, this is the telescope to view what is distant. So that observer will be able to view H1 through the unsilvered part of the mirror. That's why there is nothing like reflection at this point. It is unsilvered. So that was line 1. Now let's go to line 2. So line 2 says H is the view of the horizon as seen by successive reflection on the mirrors in position M2 and M1 respectively. So this was the horizon as seen through the unsilvered part of the mirror. Then through the silvered parts, through the reflections, you'll be able to view that H. And those are the successive reflections at the mirrors M2 and M1. So that is line 2. Now let's go to line 3. Line 3 says mirror M2 is rotated about the pivot O until the two images of the horizon in the two mirrors coincide. Hence mirrors M1 and M2 are parallel. So this shows that they coincide. This one shows that they coincide, and I think realize that this mirror and this mirror, as I was drawing it, you realize that they are parallel. So as you draw your diagram of a sextant, make sure that this line is parallel to this line. That is very, very vital for you to make these images coincide. So that was line 3. What about line 4? Line 4 says the position θ1 of the mirror M2 is noted on the angular scale. So this is our angular scale, and this is the position of M2. So we have to locate it. Therefore, we shall extrapolate and be able to read off this value. So that was line 4. What about line 5? So line 5 says the mirror M2 is further rotated so that the image of the star coincides with the horizon. So what does that mean? It implies that this one is rigid or fixed, but this one can be rotated about a pivot. So we shall put a pivot O which is there so that the mirror can rotate to a new position M2 prime, and in that position it will be able to get that, it will be able to capture the image of this star. And I think realize that this ray is constant for these two incident rays. So in this case, previously we derived that the incident ray was kept constant and the reflected rays changed. So in this case, it is just the reverse. It is this reflected ray which is kept constant, but the incident rays have changed. So the concept will be the same. So what is that concept? Let's look at it here in line 6. So line 6 we shall say the position θ2 of the mirror M2 is noted. So you come here and locate this position, read off the position of this mirror, and that will be θ2. Then next line we shall say that the angle of rotation of the mirror M2 is equal to theta, which is equal to θ2 minus θ1. So we'll come here and be able to get that angle theta. So from here to here, the angle is theta and is equal to θ2 minus θ1. So you'll come and locate your theta. And by geometry, this angle will be the same as this angle because this is parallel to this. Therefore, there will be corresponding angles. Okay, so we shall conclude that since the angle of rotation of the reflected ray is twice the angle of rotation of the mirror, it implies therefore that the angle of elevation of the star is 2 theta. So this is what we derived in the first part. In this case, it implies that if this rotation is theta, it implies that this will be 2 theta. So 1 mark for the correct setup, and here this is how the marks will be awarded. So now we shall go to part C, Roman 1. Roman 1 says, describe how the focal length of a convex mirror can be measured using a convex lens of a known focal length. So the first thing to do is to arrange our setup. So we have that object screen. The next is the lens and the image screen. So you come and say that a convex lens L1 is placed at a distance greater than its focal length from the illuminated object, and the apparatus are set up as shown. So why is this distance greater than focal length? It is because for a focal length to form a real image, the object must be behind the principal focus. Other we shall say that the image screen S2 is adjusted until a sharp image is formed on it. So adjust this screen until to and fro until a sharp image is formed. The distance x between L1 and S2 is measured. So this distance is measured. So for this slide, that is how the marks would be awarded. The convex mirror, whose focal length is required, is placed coaxially between L1 and S2. Then the mirror is adjusted until a sharp image is focused on S1 adjacent to the object. The distance y between L1 and the mirror is measured. The focal length f is then calculated from the formula f equal to x minus y over 2. So that was Roman 1. Now we shall go to Roman 2. Roman 2 says, the plane mirror P in the figure below is adjusted to a position 20 centimeters in front of the optical pin. The image of the pin in P coincides with its image in M. Calculate the focal length of the convex lens. So here there's something we need to know, is that the object distance for a plane mirror is equal to the image distance for the plane mirror. So if this is 20, they told us in this question that the plane mirror P is adjusted to a position 20 centimeters from the optical pin. So this distance is 20, meaning also from here to here is also 20. What does that imply? It implies that from the distance between the object and the image is 40, because 20 plus 20 is 40. Now when it is 40, what does that mean? It will also realize that from here up to here is 30. Now to get this remaining part, it will be 40 minus 30. So with respect to the convex mirror, to imply that object distance is 30, then image distance, like we already said, it will be 40 minus 30, which is 10. But because it is virtual, that's why you put a negative here, so the object distance will be negative 10. Then next we will use mirror formula to come up with our focal length as negative 15 centimeters. So that brings us the end of this video. Thank you for watching, and be reminded the next video will be on the test of physics paper 1. So if you are not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on test 3 of physics paper 1 has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.